Yeah. Okay, let's move on. So now what we're going to do is, well, we're going to try to make a simple additive synthesizer using several sine waves at the same time. So that should be very quick, but I just wanted you to see how to do that kind of stuff. So. And after that, we'll introduce a new operator in Faust to do delays. And with delays, we should be able to implement a lot of stuff. And after that, you'll pretty much know everything you have to know in Faust to do a lot of things. The only thing that you will not know is how to do recursion, but we'll probably do that only tomorrow. And that's definitely the hardest thing to do. For now, we're going to do a simple additive synthesizer. Okay. So in the old days, when we didn't have digital technologies and that people were using analog synthesizers, like Nando, for example, people were pretty much making sound with very simple circuits, but one of the fundamental things that people were doing was to use several oscillators in parallel to generate more complex sounds. So with what we've seen here, we artificially, with ring modulation, we artificially create sidebands by modulating the amplitude of a sine oscillator or of something else. Sorry. But another way to create more harmonics is just to have multiple sine oscillators running in parallel, right? And each of them being tuned at a different frequency, and that's what we call additive synthesis. So we're going to make a simple additive synthesizer, and that should not take us very, very, very long. It's just to show you how to do it. Okay, so I'm going to comment this code out here. So that we start over with something new again. Emma, did it do it or no? Okay. Yeah. After lunch break at 1, we can try to debug that because there is going to be a way to do it. So yeah. So for now, just yeah. Okay. So I'm going to create a new process. So there are multiple ways to do that in Faust. The only way we can do it now with what we know is by using a bunch of commas, right? So running several sine oscillators in parallel and then connecting them all together at the end. We'll see that in Faust we can do that automatically. But we'll see that later. So in Faust, we can actually create several things in parallel, tell how many we want, and not have to just copy and paste the oscillator every time we want a new one, basically, which is pretty important in some cases. So we can create loops, basically, in other words. So I'm going to create a sine oscillator, and I'm going to give it frequency. And here what we're going to do, we're going to create a harmonic series very similar to the one that we studied yesterday morning. If you remember yesterday morning, when we did the chapter on acoustics, I had this Faust code where I had checkboxes, and I was creating new harmonics every time. So we're basically going to implement that in here. So I got one sine oscillator. That's going to have a specific frequency. Then I'm going to have another oscillator, and its frequency is going to be the frequency of the first oscillator multiplied by 2. So that's what? Yep, but in musical words? Well, first harmonic, or it's the 1 octave, one octave above the frequency, basically. Okay. And if I create another one, and I say that the frequency is going to be the original frequency multiplied by 3. There we go. 3. Sorry. What?
You're not going straight in octaves.
No, not octave. So if I multiply by 3, what is it going to be? Yeah, exactly. So now I have 3 sine oscillators in parallel. So actually, if I save that, and yeah, I didn't declare frequency. So I probably want to declare frequency somewhere. So I'm going to create a frequency slider. And because I'm very lazy, I'm just going to reuse the one that I had here. And there we go. Okay, so I have a frequency slider. The only thing here is that I actually want to make sound. So I don't want like an LFO. So I'm going to set the default frequency to, let's say, 300 hertz. And the minimum frequency, I'm going to say 20. Okay, and maximum for now, just, okay, 2000. I don't really want to go higher than that because in general, sounds about 2000 hertz are not very pleasant to listen to. Okay, so if I save that, now it should work. There we go. Okay.
What is the coding figure for an LFO? You're using 20 there. Do you say that's kind of like?
So LFO are usually between 0 something, so 0 point something, and 15 hertz. I mean, there is not really any standard for that, but basically the human hearing range starts at 20 hertz. So everything that is, I'd say everything that is below 20 hertz can probably be considered as an LFO. But the thing is that the term LFO was used when people were using analog synthesizers because the way the way you design a circuit for an LFO is different than or it's a little bit different than a circuit for a sine oscillator because they don't really work exactly in the same way. So, but then in the digital world, it doesn't really matter. You can use the same sine oscillator to create an LFO than to create a very high frequency oscillator, as long as it's a sine wave. If it's not a sine wave, then you might want to use a different kind of oscillator to create an LFO than to create a high frequency oscillator because of aliasing. But so if I look at the block diagram of that, that's not really what I want to do, right? Because right now, I have 3 sine oscillators in parallel with 3 different outputs. So what's going on right now on your computer is that one output is probably going to one speaker, one output is going to another speaker, and the third output is probably lost in transaction. So that's not what we want to do. Here, we want to add all these guys together. So to do that, the simplest way to do it in Faust, so we could just put adds in here if we wanted to, right? And that would work. So if we were doing that in C++ or in a normal programming language, that's what we would do. But in Faust, we're not going to do it that way. Because in Faust, we have the merge operator that we studied yesterday, okay, if you remember that. So we're just going to do merge into one signal, okay? So it's probably going to clip, exactly. So if I save that and I look at the block diagram now, there we go. It's doing that we want. So we're merging the 3 signals together. Okay. So as Richard said, the only problem with that is that it's probably going to clip. Maybe not. It depends on the cases. But yeah, it basically depends on the frequency of the sound that we're going to use. You know, so for some frequencies it might not clip, but for other frequencies it will probably clip because. What's going to happen is that the different sine waves are going to add together, you know, and if they are in phase, well, because one sine wave here has a gain of 1, then it will click. So it's we should be careful. Should be careful with that. So we could scale the gain of these guy, you know, and probably divide it by 3, for example, to make sure that it's not gonna click. But I mean, for now, we're not gonna do it. What we're gonna do instead is that we're gonna put a gain slider at the end of this algorithm in here, so that we can just change the gain manually. Okay. So here we're gonna multiply the output of the addition of these 3 sine oscillators. We're going to multiply that by the output of the gain slider so that we can control the gain of our little synthesizer.
Question, Romain.
Yeah.
Which one has a gain of 1? You said that one has a gain of 1. Yeah.
They all have a gain of 1.
Oh, that's right.
Yeah.
Okay, great.
Because by default, the sine oscillator in Faust has a gain of 1. So they all have a gain of 1. So there are very good chances that at some point the output of that is 3. So that the range is like between 3 and -3, which is way too high. So that's why we need to scale the gain. So I'm going to create a gain slider, okay, just by doing that, right? So do a multiply, parenthesis, and then gain. And I'm just going to create a new slider. I'm going to call it H slider. Gain. And default value, I'm going to say 0.3. Minimum 0, maximum 1. And a step of 0.01. Okay, so now if I save that, I'm going to have a gain slider. Very good. And if I look at the block diagram, that's exactly what I wanted, right? So merging the 3 outputs together and multiplying them by a gain between 0 and 1. Very good. So if I look at the spectrum of that, so I need to make the connection in Jack. There we go. Okay. So if I look at the spectrum of that, I get 3 harmonics, right? And those are the 3 sine waves that I created in my Faust code. So now we'll notice that if I increase the gain, oh, what's going on? There are a lot of harmonics. Why is this happening? Absolutely, that's exactly what's going on. So what's happening in here is that okay, if I have my sine wave and the signal of my sine wave is out of range, and let's say that it's between 2 and -2. So its gain is between 2 and -2, okay? The computer is very stupid, so it's going to get rid of everything about this limit and below this limit. So everything below -1 and everything below above 1 will be discarded. So now my sine wave is not a sine wave anymore. It's a weird square wave. And because my weird square wave has very sharp edges in here and here and here and here and here and here, it's creating more harmonics. So the spectrum that we're seeing in here is more the spectrum of something close to a square wave than the spectrum of 3 sine waves added together. Okay, and that's why we get that. So that was just, you know, as a quick reminder. Okay, so we have that. We have frequency. We have gain.
Can you see the code real quick?
What?
Can you see the code real quick?
Oh yeah, absolutely. Yeah. There we go. So we have a slider to control the frequency. We have a slider to control the gain. Now we're going to introduce a new user interface element, which is going to be a button. So very often, yeah, sure.
Somebody has the stuff ringing.
Oh yeah, it's me. Okay, so I'm going to add a button so that when I click the button, there is sound, and when I don't click the button, there is no sound. That's pretty important to do that in general in user interfaces. So in Faust, it's very, very easy to do that. I'm going to create a new variable, and I'm going to call this variable gate, because that's basically a gate that we open or that we close. And I have a specific user interface element in Faust to create button, and it's called button. Okay, button only takes one argument, and this argument is a name. So I need to give a name to my button. And for instance, here I'm going to call it gate. Okay. So then I have to use gate somewhere in my code, because I'm not using it anywhere for now. Okay. So I could just use it after gain or with gain, you know, by simply multiplying my gain by gate. Okay. And here I don't have to put parentheses, right? Because the multiply already has two arguments. One argument on one side, one argument on the other side. Okay. So now if I...
What you're saying then is that button has two values, 0,
Absolutely.
0 or 1.
So button creates a signal. Just like everything in Faust, when the button is pressed, the signal is 1. When the button is not pressed, the signal is 0.
Is that like a toggle, or is it just literally as you physically push it?
That one is a button, but there is a toggle too that we can use. So now I have a button in my interface, and if I click the button, I get sound when I want to. So I almost have a synthesizer now. Okay. So there is only one little issue though with this design. Is everyone good with the code, or? Yeah? Okay, cool. So I don't know if you noticed that, but when I click the button, what happens? There is a click. That is very easy to see on the spectrogram, because every time I click the button, I see that there is an impulse created across the frequency axis. I mean, maybe it's fine. Maybe it's a feature, you want to keep that, and that's okay. It's just a very sharp attack, because what happens here is that the wave is being generated all the time. So if I draw the wave, and if the wave that I was controlling with my button was a sine wave again, okay, that's the sine wave. So the wave is always generated in the background, okay? But depending on when I'm going to click on the button, if I get lucky, which is possible, if I get lucky, I might press the button just right here, okay? And if I press the button just right here, then I'm not going to have a click, because my sound is going to start at 0 and slowly increase up to 1, you know, and then I'm going to generate the sound. If I get unlucky, which is probably what's going to happen most of the time, because there are very little chances that you manage to press the button right here. I might just press the button right here, and then what is going to happen is that I'm going to go straight from a signal that was 0 to a signal that is 1. So that's an impulse. And if you listen to it on speakers, it's okay, but if you listen to it in headphones, it's very ugly. So I want to add what to my synthesizer?
Smooth.
That's one way to do it. I have to add some kind of envelope generator, basically. Yes, some kind of envelope generator. So the most common kind of envelope generator is like ADSR or ASR. So ADSR is for attack, decay, sustain, and release. You know, here, because I'm very lazy, I'm just going to add a smooth. And my smoothing function is going to be a very decent envelope generator. And it's probably actually going to be even better than an ADSR envelope generator in some ways, because the attack and the release are going to be exponential attack and exponential release. Because my envelope, the smoothing function does things exponentially, basically. And can someone tell me why it's good? Well, it's because in the real world, that's how things happen in the real world. Like in the real world, if I have a string on a guitar and I drive the string on the guitar, the amplitude of the sound of the string is going to decay, and the decay is going to look like that, right? It's not going to look like that. An ADSR envelope generator usually does that. It creates a linear decay. But in the real world, linear decays don't exist. Everything happens in the logarithmic world, so things decay that way and not that way. My smoothing function is going to create a linear exponential decay, and that's better. There is, I don't think there is an exponential ADSR, but there is a regular ADSR with just attack. Well, you know, one way to make it exponential is to connect the ADSR envelope generator to a smooth, basically, and then you're going to make it exponential, basically. That's and in terms of computation, I don't think that it costs more to do that than to actually implement an exponential decay. So the way I'm going to do that is, I'm going to do it the dirty way here. I'm just going to connect the output of my button to a smooth, okay? And I want to be able to control the attack and the release time of my envelope generator. So my envelope generator here is literally the smoothing function, right? I'm not going to be able to control the attack time and the release time separately in that case, right? The attack time and the release time will be the same, which is fine. So to do that, I'm going to reuse this other function that we studied yesterday, which is tau to pole, so that we can give a duration to the smoothing function and not a pole, because that's more convenient. Okay, and okay, I'm going to call it T. It's a bad name. So then I'm going to create a new slider for that. And this slider, I'm going to call it, at release. Okay. Just going to say that it's in seconds. Okay. And minimum value, very, very small. 0.001, because this is in seconds. So I really want to be able to control things in the milliseconds world. Okay, and actually, so that's the minimum. So I need to declare a default value, and a default value, I'm going to say 100 milliseconds. So 0.1, okay. Maximum 2. It's going to be very long if I do that. And then a very precise step of 0.01. Okay, so now if I save that and I press the button, here we go. I don't have clicks anymore, and now I have don't have a click, and I have a very simple envelope generator running. If I increase this value here, so you probably noticed that even though we said that the duration here is 1 second, it actually took more than 1 second to decay. It's because of floating points rounding errors. Why? I'm not sure I want to tell you why. Because that's might take a little bit of time. All right, very quickly, the reason why this is happening is because of that. It's because, I don't know if you remember yesterday, but the interpolation of our filter only kind of starts happening if we are at 0.99, all right, there, basically. So it means that all the precision that I'm going to have to control the interpolation time is going to be between that and that. So that's a very small range. So it means that I don't have a lot of precision in here. Depending on the number of bits that are used to kill my floating point value, basically. So things are heavily rounded in here. And because things are heavily rounded, I get errors, and the values that I'm defining here might not be the right, exactly the right value. So just to tell you. Anyway, yeah, that's it. So back to the Faust code of this thing. Here I named frequency freq. I named gain gain, and I named gate gate. That's actually important. Why? No, there is actually a reason. That's a Faust standard that you should remember. So some Faust architectures, not all of them, but some of them are MIDI compatible. If you want your Faust object to be associated with MIDI parameters, then your frequency parameter has to be called freq. Your gain parameter has to be called gain, and your not on, not off parameter has to be called gate. Okay, so it is the responsibility of the developer of the Faust architecture to make sure that the MIDI data that you're sending to your Faust object will be translated into a frequency. So we don't do that on the Faust side. So in the case you plug a MIDI keyboard to your computer and you're using a Faust architecture that is MIDI compatible, the developer who implemented the architecture file should have a function that turns a MIDI number into a frequency already. So you don't have to worry about that. Gain should be already turned into logarithmic gain. So the MIDI numbers that you're getting for the gain that are between 0 and 127 should already be translated so that they are between 0 and 1, and should already take into account the fact that this is a linear gain and not a scale in dB in here. Okay. And then same thing for not on and not off. The developer who implemented the architecture files should have made things so that the gate parameter is controlled by not on and not off evens. Okay? So in theory, if we had a MIDI keyboard and we were using MIDI compatible architecture file, this should work with a MIDI keyboard. And that should be ready to go, basically. The label. The variables, the variables might even be ignored here in that case. What matters is the label. So not the name of the variable, because on the C++ side, this is turned into something else. So when your Faust code gets compiled into C++, if you look at the C++ code, freak, gain, t, and gate don't exist anymore. They have, yeah, exactly. So, so what matters is really the name of the parameters that you're using here.
Just to clarify for gate,
Yeah.
does it actually expect a 0 and 1? Like the architecture?
0 and 1, absolutely. So on the architecture side,
We'll translate from no, not, no, not.
absolutely, yeah. So it means that because things work like that, it's your responsibility as the Faust developer to implement the envelope generator, basically. Okay. So so the trigger of the envelope generator should be a parameter called gate, basically, and the velocity of your MIDI note should be a parameter called gain, and its value on the Faust side should be between 0 and 1. And then the pitch of your note should be a frequency, and the name of the parameter should be freak. Those are standard things. If you don't do that, it's not going to work. So, so you really have to pay close attention to that. So not all Faust architectures are MIDI compatible. It's up to the developer who makes the architecture file to take care of that. Yes?
So for example, so for freak, would
Yeah.
that in C++, would that turn to like an accessor function that already has boundaries for 20 to 2000?
It's up to the, so on the C++ side, what's going to happen is that all the parameters that you declared in here and that are visible in the user interface will have a pointer to a variable inside the callback function associated with them. So, so basically, freak is going to be a pointer to the frequency parameter in the callback function. Same thing for gain, same thing for gate. So you have total control on what you, like on the C++ side, you have total control on what happens at this level, basically. So just give it whatever you want, basically.
So the 20 to 2000 is just strict?
It is. It depends on what the developer did, basically. So the developer can have access to these values, basically, and know what the person who wrote the Faust code decided for the range. But he can also choose to ignore that. So what I'm saying is that on the C++ side, you have total control on the frequency parameter in the callback function. So you can choose to ignore all these informations if you want, basically. But you can choose to not ignore them and to take them into account if you want to. But that's the responsibility of the architecture file developer, basically. So it's very flexible. Like you, it's totally up to you. People who use Faust in the industry to generate C++ code, they don't look at that. They totally ignore that kind of stuff. You know, like they just take the address to the variable associated with frequency and change it basically directly. You know, and that's yeah.
So you use this for testing standalone, and then you can, without modifying the source, you can plug it into the thing.
Yes.
Compile it differently and run the same thing.
Yeah. I mean, you know, all these things are open source, so you pretty much do what you want. So,
I mean, the intention is so that you can test the stub on its own from the screen, but then you plug it into the instrument and the same code.
absolutely, yeah. Actually, all right. So maybe it's we're just going to take a little break with that, and I'm gonna. So I know that some of you don't know C++, but I'm just going to take a little break of 10 minutes to look at the C++ code generated by Faust, because I think it's interesting for some people here in the room. So for that, I'm going to create a very simple object, because otherwise it might be a little bit hard to look at it. But this thing works. We don't really have anything to add to it. I will post it on the website, and that's we're done with that. So I'm going to comment it out. And I'm going to create a very, very, very simple Faust object, which is just an object taking an input signal and outputting it, okay? And I'm going to compile that to C++. So I save it. To do that, now I have to go to my terminal. And I'm going to go to the location where this file is stored, and it should be in here, okay? So I got d2.dsp, which is this guy here, okay? And my d2.dsp is just take the input signal and I output it, basically, okay? So to look at the C++ code, I'm just going to do Faust d2.dsp, okay? And then I'm going to say -o and d2.cpp. Boom. So now I have a C++ file in this folder. I will open the C++ file and look at what's in it. Okay. So the C++ code generated by Faust in its most simple case is just a big class, okay, called myDSP, okay? We're declaring a specific type, which is a Faust float, which is just a float, basically, okay? So, so I'm just calling Faust float in the callback function, but Faust float are just float, just so that you know. So all this shit here are metadata that were declared in the libraries that I called in the Faust code, but that I should just, you know what? I don't need them. It doesn't matter because in they are not calling any objects. It's just that they are. Okay, so I'm gonna recompile that. There we go. Okay. So this class has several methods. There is the metadata method. The metadata method is most of the time very useless. Metadata were declared by the people who wrote the libraries, you know, or by yourself, you know, to put stuff like copyright or license, you know, or things like that. So that method should be totally ignored. Then you have a method that gives you the number of input of the object, which is 1, okay? It's true. Our Faust object only takes 1 input. Then you have another method that returns the number of output, 1 output, okay? Then you have, so those two, we should ignore them because they are both called by init. Okay, so we have an init method. The init method calls 2 sub-methods that are class init and instance init. So this method here should be called by the architecture programmer, basically. So the guy who designed the Faust architecture, or the person who is using the C++ code should call the init method. Okay, and the only argument that he has to provide to the init method is the sampling rate of the system, okay? So then the sampling rate of the system is copied into a global variable that is in here, and that can be used later in the callback function, okay? So the developer should call the init function to provide the sampling rate, basically, okay? Then we have this method called build user interface, okay? This method will contain all the user interface elements that I potentially declared in my Faust code. The Faust code that I'm created here doesn't have any user interface elements, so it's pretty empty. That one is just like a default container, so a default group for my objects. But if I was creating a slider, then I would have interface and then add horizontal slider, you know? And that can be called by the person who's designing the architecture file to create a new slider. And then this guy is responsible for the implementation of the slider, basically, okay? And finally, I have the callback function. The callback function, which is the compute method in here. The compute method takes 3 arguments. The first argument is basically the buffer length. Okay, it's the buffer length. The second argument is the input. So the input is a double array. One dimension is the buffer, basically, and the other dimension is the channel. Okay, so I can have as many channels as I want, and I can have buffers with any size that I want. And then I have a last argument, which is the output buffer with the different channels. Okay, so things are not interlaced like on iOS or anything like that. I have one array for each channel, and each channel has a sub-array for the buffer. Okay. And then I have my callback function, and so my callback function is just creating pointers to the input variable that I have here. And my Faust code knows that there is only one input in here, so it's taking the first channel because there is only one input, and it's creating a pointer to the output. But only the first channel, because there is only one channel for this Faust object. And then I have the function in here, that is just count is the buffer length. So I'm incrementing the buffer length, and input I, so input 0, okay, which is the copy of the first channel, gets copied into the output, and that's it. So it works. Just to it was just to show you. So it's pretty straightforward. And then if you create more complex things, Faust might create other methods that will be called in the callback function for some elements, like a sine oscillator might be outside of the callback function and declared as another method, basically, or things like that. But most of the time, you end up with a giant compute method with everything in it, basically, and that's it.
If there are delays, what will appear in this code?
So there was a delay. What would happen is that Faust would create, in private here, Faust would create an array that is basically a buffer where your delay would be stored, basically. So Faust automatically allocates memory if you create a delay for your delayed signal, basically. Okay? Yeah, Jason.
For shits and giggles, can we see the last example?
Oh yeah, sure. Yeah, very good. So I'm gonna get rid of that. I'm gonna remove the comment. I'm gonna save. Okay. And so now it's more complicated because we see that Faust created a subclass in the class. And that's probably my sine oscillator. Okay? So I have my sine function in here, basically. Sin f. Okay, and then now I have a bunch of variables that were created. Okay. And I have a lot of stuff in the metadata, and I see that those stuff are just like versions, licenses, or things like that. It's just things that are not that helpful. Then in the instance init called by my init function, Faust allocates the memory for all the stuff that were created in the private section of the class. Okay, and it's doing it the old way, as you can see. So that's being called when you start your plugin. And then build user interface. So build user interface now has add horizontal slider, okay, add button. And I see that add horizontal slider has a string for the parameter name, but it has an address to pointer to a weird parameter name, which corresponds basically in that case to the attack release time in the callback function. Okay, so I can have access to that and just modify it with whatever I want, you know. And then the programmer can decide to ignore this value, this value, this value, and this value, or to not ignore it, basically. The thing is, the Faust distribution comes with a bunch of libraries that can be included to that, and then makes all this thing a little bit higher level so that you don't really have to call that, and it can just like give you that directly, basically. And that's part of the Faust distribution. And then the compute method here, yeah, it does all the initialization step, and here is the callback function. So now it's harder to read, because as you can see, all the variable names that I created in the Faust code don't exist at this level. And they were replaced by something else. Does that make sense, or?